Yes, I do. Can you see me? Hello. Okay, great. So now, so it's a pleasure to be here, at least in a weak sense, and there are many familiar faces. So hi to all of you. Um, okay, so let's go to the presentation. So I would like to start by thanking the organizers for inviting me to this workshop. I'm sure they didn't anticipate what would happen. And so the organizers are actually also my co-authors, or some of them, Larsen and Tiep, and Bob is also an organizer, and now Martin Liebeck. So it's a pleasure to thank all of you. And okay, I'm going to talk about subset products and applications. Now let me start with some definitions. So G is a group, usually a finite group, and AB are subsets, and the subset product is simply the set of product of elements from the first set times elements from the second set, and then the same is for longer products. Now. So okay, so G will natural in our case G will often be a non-abelian finite simple group, but I would like to start with the background. Natural questions about subset products is to study the size of the product and when is the product equal to G. It's a covering situation, and also we will be sometimes interested in distributions associated to the product. So let me give you some background and convince you that there has been a lot of activity in this topic in the last 2 decades. And there are some deep theories involved. So one of them is the theory of approximate subgroups and the product theorem. So this was done, it started with the result of Helfgott on PSL2P, and then there was a product theorem independently by Breuillard-Green-Tao and Pyber-Szabo. And essentially, it says that if we take a finite simple group of bounded rank, there is epsilon depending only on the rank, such that every generating subset in 3 steps, either it expands, namely the size of A cube is at least the size of A to the 1 plus epsilon, or maybe there is not enough space to expand, and so another case is that A cube is already the whole of G. So that's a very deep theorem, and there are various more elements of this interesting theory. So except the people who proved the product theorem and Helfgott, there is also important contribution of Udi Horoshovsky using model theory. Okay, so that's one context where we meet products of subsets. Now another context is that suppose G is any finite group, and mg is a minimal degree of a non-trivially reducible character, representation of G over the complex numbers, say, and okay, and a family of finite groups is called quasi random if mg tends to infinity as the size of G tends to infinity. Okay, so a useful example for us is to take for F the family of all non-abelian finite simple groups. Our simple groups will always be non-abelian. So it is well known, people have studied a lot representations of finite simple groups, and it is a well-known corollary. Okay, so now there is a famous Gowers trick. Well, what happened? Gowers developed his theory of quasi-random groups, and he was mainly interested in product-free subsets. But and then I think even before Gowers' paper was published, Nikolov and Pyber noticed that one of his results implies what's written here. So it means that if you have three subsets of a finite group, which such that the product of their sizes is quite big in the sense that you see on the screen, it must the size of the group cube divided by m of g, then there is covering. ABC equals the whole of G. This is a wonderful result, and it has been used for many applications in many situations. And there are some obvious consequences. For example, if you're interested in kind of covering by powers of one subset A, then obviously the situation is that if the size of A is at least mg to the minus 1/3 times G, then A cube is G. So it's a covering result in 3 steps. And if we have F for F, a quasi-random family of finite group, and there is epsilon greater than 0 such that ABC are large subsets of S, namely of proportion at least epsilon, then what's happening is that ABC is again the whole of G, provided G is sufficiently large. So we get a covering result in 3 steps for quasi-random families, and obviously this applies for the family of finite simple groups, which, as we said, it is quasi-random. So these are very strong results. There is a bit of a problem because sometimes we want to know about products of 2 sets and not 3 sets. So all these theories don't tell us much about the product of 2 sets, and sometimes for good reasons. Sometimes you cannot say much. We'll see. So can we extend the results on product length of length 3 to product of length 2? So this is the main challenge of the talk. Usually not. There is no growth. I mean, obviously, for example, if you take a generating set, which is not the whole of G, then there is growth in 2 steps, but it could be a very small, unnoticeable growth. And also, there are not nice covering results. A rare situation, which is an almost trivial situation where we get good results for covering by 2 subsets, is simply if the subsets have size which is more than half the group order. So you see the whole sophisticated argument on the slide. In this case, AB is the whole of G. And actually, we will need this trivial result towards the end of the talk. So sometimes even trivial things help. But of course, this is not enough. And then in our case, we want to check whether if we pass to normal subsets, things get better. So normal subsets are close under conjugation, and therefore they are just this joint union of conjugacy classes. In particular, conjugacy classes are normal subsets, and there is also a lot of interest in products of conjugacy classes, for example, in the context of Thompson's conjecture, which I mentioned briefly. So what if we deal with normal subsets? Does it make things better? And so in one sense, there is already an indication, a result with Martin and my ex-student Gili Schul shows that if you have 2 normal subsets of a finite simple groups which are not too big, so they should be of size most G to the delta, then the product is for some positive delta, the more kind of if it's very close to 0, then the situation is better. But there is really very big expansion in 2 steps for normal subsets of arbitrary finite simple groups. So the size of R times S is the size of R times the size of S times 1 minus epsilon, where if we fix this epsilon, if we aim it, the 1 minus epsilon to be 99%, say then there is some positive delta which ensures this. And if you are mainly interested in subsets in power in square of one set, then you get that R square in this case is almost the square of the size of R. So what's nice about this? Of course, it's easier to deal with normal subsets. It's not a trivial result, but it's not as deep as the previous result which I quoted. But here, unlike in the product theorem, for example, this holds for all finite simple groups, not just of Lie type of bounded rank. And we have a 2-step growth and not 3-step growth. And the 2-step growth is really more or less maximal and faster than the 3-step growth of non-normal small generating subsets in the product theorem. Okay. So this is one indication that maybe if we assume normality of the subsets, more can be said, and but this tells us nothing about 2-step growth or covering of large normal subsets, because you see the whole assumption here was that our subsets are of size at most g to the delta, and we want actually our main goal is to understand large normal subsets and not small normal subsets. So let's move to the next slide. So I already mentioned the conjecture of famous conjecture of John Thompson, which is actually an evidence that some 2-step covering problems by normal subsets are notoriously difficult. Okay, so probably you all know Thompson's conjecture. I feel stupid to tell you about it. So every finite simple group has a conjugacy class whose square is a whole group. Now this conjecture implies or a conjecture that every element of a finite simple group is a commutator. Or a conjecture was proved in 2010, but Thompson's conjecture is still open. The best result is Ehlers and Gordeev for groups of Lie type over fields with more than 8 elements. If the field is tiny, it is still open and very challenging. Okay, so let me just mention briefly some approximations of Thompson's conjecture. Okay, so there is a result of mine from more than 10 years ago that it's kind of a random or probabilistic approximation, if you like. It shows that if you take a random element of a finite simple group and you take its conjugacy class, then its squares is almost everything. We don't know that the square of the class is everything, but it's almost everything. And actually, you see my computer, so I suppose you see me doing this, right? Anyway, I cannot hear you. Speak loudly. Okay, great, thanks. Okay, so that's but of course it's much easier to prove almost covering than covering. So but that's one small step. Another not so small step is in a paper with my current co-author also, Michael and Tiep, that large enough finite simple groups satisfy a slightly weaker version of Thompson's conjecture that you can always choose 2 conjugacy classes, not the same the way we prove it, but very, very different in a way, orthogonal to each other. 2 conjugacy classes whose product is not everything, but it's everything but the identity element. So it's this one. I hope this will. Yeah. Okay. Now, anyway, in my result with Larsen and Tiep, we needed the groups to be so large, you see, of size greater than 2 to the 630, which is really ridiculous, And Bob Guralnik and Gunter Malle improved it to all finite simple groups. They also used computational group theory, of course. So these are quite nice approximations, but we are still far from a proof of Thompson's conjecture. Now let me give you you think it. Oh, sorry. Yeah, I think now it's better. Maybe in the last minute it would be optimal. Okay, so let me give you now some motivations why are we interested in normal subsets of finite simple groups? So some context where this rise up. Okay, so the theory of word maps, you heard a lot about it in recent years, and I will. Oh, is it?
Just a moment.
Okay, thanks. You should thank Lena, the computer expert who is next to me. She's doing the hard work. Okay, so a word is just an element of the free group. We usually take non-trivial elements, non-identity, and it defines a word map on every group simply by substitution, and the image of the word map on a group G is called WG, where W is the word, and this is obviously a normal subset. There is actually also a criterion by Alex Lubotsky which subsets can be obtained, and there are various. Nowadays, it's quite a developed theory. The roots go back to Borel about dominance of word maps, and some relevant results are again with Michael and Tiep, one from 2011, that if you take two words which are non-identity, or it could be the same word, of course, and you take the image of them and you multiply the images, then you see that the product is G. Previously, we had a result with 3, and previously also a result with Martin with some bound, but 2 is best possible. And so you see, this is a normal subset, this is a normal subset, and we have a covering result like this. And another result from 2019 with Michael Tiep is again, we are looking at 2 words in these joint sets of variables now, and we show that they induce an almost uniform distribution on finite simple groups in the L1 norm. And now a question is, can we extend results like this to all large normal subsets? Maybe the reason that such result holds has nothing to do with words. Maybe every large normal subset will behave nicely like this, or 2 normal subsets. So this is one motivation, and there will be more. And let me now actually formulate the exact questions which we want to address. So ST are normal subset of a finite simple group, and now suppose they have positive proportion. Okay, so the finite simple group its size may go to infinity, but the proportion is bounded away from 0. It's at least epsilon. By the way, this doesn't happen usually for word maps. It happens in bounded rank, but in this case there is a positive proportion. It's a result of Michael Larsen, but usually the images of word maps don't even satisfy this. So question 1 is: does ST contain all the non-trivial elements of the group G if G is sufficiently large? Okay, so there is a reason why we exclude E. We will see it. So this is a covering question in 2 steps. Now another question is that is a distribution for G in G. Again, non-trivial. We want to count the number of representations G equals ST, where little s is in big S, little t is in big T, and it would be very nice if this kind of distribution will be close to uniform in L infinity, not just in L1. So this is exactly this question. Regardless of G, it should go uniformly to a uniform distribution in L infinity. It should, but maybe wouldn't, but we'll see. Okay, question 3 is what happens in the special case where the two subsets are similar? You will see that sometimes it's a different ball game. It was a surprise for us. And question 4 is about applications. Okay, so comments. So let me see. First of all, why we exclude E in questions 1 and 2. So essentially, you can see here the reason. Essentially, we can easily show that there is a conjugacy. There is a normal subset of size. Certainly at least epsilon G. It's even between 1/3 or 2/3 of G, and we can then take T, which is a complement of S minus 1, and then we have that T is also large with a large epsilon even, and the identity is not in S. So we have to drop the identity of the game. Now I'm also saying that assuming that ST are normal subsets is necessary in these questions. There are negative answers if they are not normal. So basically, I'm not going to detail. It's very simple, but you can see it. But basically, even question 1, which is weaker than question 2, has a negative answer with non-normal subsets. Sometimes not just E is missing, more elements are missing from S times T. Okay, obviously a positive answer to question 2 implies a positive answer to question 1. This is why we like L infinity and we hate L1. And okay, and let me see. Okay, and now I will jump and give you immediately all the answers. But what I want to say is that initially our intuition was that at least to question 1 there should be a positive answer for all finite simple groups, and this is what we try to prove. The drawback is that it's more time-consuming to try to prove wrong results. Though some people succeed, and so here are the main results, which some of them were surprising to us. So the answers to questions 1 and 2, covering and distribution, are negative if G range is over all finite simple groups. It's negative even for alternating groups, and it's negative even for projective special linear groups. So life is not ideal. Okay, what happens in S equals T case? And the answer to question 2 about the almost uniform distribution in L infinity is still negative for alternating groups. But now we come to good news, some positive results. In the case S equals T, when we have just one normal subset and T say, and we want that T square will be everything, one large normal subset, then the answer to question 1 is positive for alternating groups. And if G is a group of Lie type of bounded rank, then we are in the ideal situation. The answers to questions 1 and 2 are both positive, and obviously also question 3 for S equals T, it's also positive. So the ideal family of groups in this context are the groups of Lie type of bounded rank. Okay, so that's the main result, and I will now go into a little bit more detail about the various groups and more refined results about them. So for example, for alternating groups, what we have is the following, that for every ST with S time plus T at most 1, we can find normal subset Sn and Tn in An. Sn is a very bad notation because, Sn is not contained in An. Such that the proportion Sn over An tends to S, Tn over An tends to T, and Sn Tn, not just that it doesn't cover the identity, this is expected, but it doesn't contain any 3 cycle. So that's a counter example for alternating group to question 1. So for example, according to this theorem, we can even take epsilon, which is arbitrarily close to 1/2. So the sizes of S and T are very close to 1/2 of the size of An, and this is not enough for ST to cover everything but the identity. So that's the bad news, but now for S equals T, I already told you that there are good news, but as you see, we have epsilon which goes to 0. We can take epsilon which goes to 0 rather fast with the order of G. So the situation is in the theorem on the bottom of the screen. So you see that epsilon here is it's very close to e to the minus n to the 1/4. Okay, so alpha should be a little bit less than 1/4, and then we are lucky. So whenever we have a normal subset of the size you see, then it covers, its square covers everything. In this case, we also don't move the identity. T square is the whole of the alternating group. So let me give you a brief sketch of the proof. It is very much related to previous work of Michael and myself about character bounds for symmetric groups. Okay, so this is, I think, from 2008, and essentially we define a certain invariant associated to a permutation in Sn, and it is well defined. I don't have time to define it precisely, but it has the properties that the character value at sigma is bounded in absolute value by this power of the degree of the character. Okay, and we have a little O of 1 also. Okay, so and this is essentially also best possible in many examples. So you can improve this sigma, but the next step is that if E sigma is less than 1 square, then if you take the conjugacy class of sigma in Sn, then its square is An, provided n is sufficiently large, of course. So what we see here is that we get already some covering by a square of a certain conjugacy class. It's a conjugacy if under this assumption, and it's a conjugacy class in Sn, not in An. So, but we are approaching what we want. Now, it can be shown that if you have a subset, not necessarily normal, even if you have any subset of alternating group of this size, this was also the size in the theorem, with alpha less than 1/4, and you pick a random element of this subset T, a random permutation, but in T, then it satisfies E of sigma is less than 1/4 almost surely. Okay, and hence we can deduce for our normal subset that there is a sigma in it whose conjugacy class in Sn, the square of it covers An, is An for n large. Okay, and now there is a little thing that, we want it to be. This is not a normal subset of Sn, it's a normal subset of An. So sometimes this is different conjugacy class, but it's not a big deal if we use some facts from Erdős-Turan statistical group theory of permutations. It's one of the foundations of this field. So we can use some relevant results and conclude that T square is an for n sufficiently large. So these are the ideas for alternating groups. We have to work harder for other groups. So let me start again with bad news, classical groups. So if we take, for example, PSLN Q for Q fixed and N unbounded and co-prime to Q minus 1, so we don't want center in SLN. So here question 1 has negative answer. There are normal subsets large of size at least epsilon g, such that no transfections lies in ST. So we don't have covering except the identity. Okay, and now, but something can be said about three subsets in the construct of finite simple classical groups. So we can when we don't have nice results for two subsets, we can look at three subsets, and of course for three subsets, if they are large enough, then RST is G for all finite simple groups. It's because finite simple groups are a quasi random family. But here is a result with epsilon, which is much smaller than what is given to you by Gowers trick. So epsilon here is G to the minus delta. And the theorem says that there exists a fixed positive delta such that if we take a finite simple classical group and we take normal subsets RST of size at least the size of G to the 1 minus delta, then this is already enough to conclude that RST is G, and this is just to convince us that it's stronger than Gowers 3. And the idea is another very important development in character bounds, and this is a Guralnik-Larsen Tiep theory of character levels and character bounds. So they actually prove a result which is already quite close to this, and to prove this result, what we use is there are two ingredients. One is a certain result saying that if the centralizer is quite small in this sense, and the character value is quite small in this sense, and combining this with a Witten zeta function, which encodes character degrees, and we have to know things about its of convergence, some which were studied by Martin and myself. If we combine these two ingredients, it leads to a proof of this result. Okay, now maybe the main good news is the bounded rank theorem. Why bounded rank behave well? And because in this case, I remind you, all the answers are positive. So let's have some notation if we take subsets of a group G and an element little g, and so PST is the relevant probability measure on G. So the probability is that if we take a random element from this and a random element from this, then we get G, and so we have a distribution. And the theorem, the main theorem in bounded rank, is that when we have such a group of bounded rank, and Q goes to infinity, of course, and we fix epsilon and ST are normal subset of size at least epsilon G, then this distribution PST is very close to the uniform distribution on G in the infinity norm. Okay, so this is what we wanted. It implies all the other things. And in particular, it implies that questions 1 to 3 affirmative answers. Okay, now let me say something about ingredients of the proof. You know, this conference is about connections with the geometry and combinatorics. And, so we have combinatorial arguments. We also have geometry in the form of algebraic geometry. So and you know which of the three of us is the expert, and it's not me. Anyway, so the algebraic geometry, essentially we use things which were used a lot in word maps, but they're a little bit technically, a little bit improved and more technical now. And so we use Lang-Weil theorem to estimate the number of rational points in reducible variety, but there is also a certain notion which is important for us when an algebraic morphism of varieties respect products. And so I will not go into details, but this is one ingredient of the proof, and another ingredient is much more classical and ancient. It's this famous result of Frobenius that for conjugacy classes, you know, this is the probability that little g is a product of random elements from C1 times random elements from CK. So this probability has a character theoretic expression, and we all know this formula, and I suppose almost all of us also use it often. So these are some tools in the proof of the bounded rank theorem. And now let me give you some applications. So first, more easy application, but I don't see how to prove it in a different way than the current proof. So first, let me remind you of, so this is an application to word maps. So again, we have a word W, and we have the word distribution defined like this. So this is a probability to get little g if you substitute random group elements in the word. And let me recall another result from the 2019 paper with Michael and Tiep, that we wanted to get a uniform, almost uniform distribution with respect to L infinity, but the price was to allow very long product depending on the length of the word. So given the length of, or upper bound for the length of the words, and you take words in disjoint variables, and you take the product of all of them, so that there exists, and depending on the length, such that this thing will be almost uniform in L infinity. This is a quite painstaking proof, and there are applications to geometry also, if you or representations, if you look at representation varieties and intersection of geometry and representation, for example, in other fields, one-relator groups, etc. But I'm not discussing this result now. What I want to say is that if we change the probabilistic model a little bit, and if we apply the bounded rank theorem, then we obtain almost uniform distribution in L infinity much faster, namely in 2 steps instead of this huge number of steps. So more specifically, the corollary is that if we take 2 non-trivial words in FD, and you have a finite simple groups of Lie type of bounded rank, then PW1G, W2G is almost uniform L infinity. Okay, and you see here it's a different model. Here you you choose random elements, random group elements instead of the variables, and here you simply choose at random uniformly element from W1G and another element from W2G, and then you multiply them. So it's a different distribution, but it's nice that we jump from, in our result here, n of L was roughly L to the fourth with a huge constant, and here it suddenly jumps to 2. Of course, it's an immediate corollary of the bounded rank theorem, and the fact that these are of size at least of epsilon g. This is a result of Larsen. Okay, so this is a modest application, and there is a version for classical groups of unbounded rank. In this state, you need 3 steps to make the distribution almost uniform in L infinity. Okay, now another application which is more ambition is related to derangement. So we take, now we are moving to the realm of permutation groups in general, and so subgroup of Sn, and the derangement is simply a fixed point free permutation. And of course, this is a classical topic studied already in the 19th century. So Jordan, for example, showed, I think it's Jordan, that if G is transitive and is at least 2, then there is a derangement in G. This is a corollary. Sometimes we teach it as a consequence of the non-Burnside lemma, right? Anyway, Cauchy-Frobenius. Now, there is a very nice result of Peter Cameron and Aryeh Cohen that the proportion of derangements in G, and recall now G is not a finite simple group, it's any transitive subgroup of Sn. So the proportion of derangements in G as above is at least 1 over n, and this is sharp. It's kind of a Frobenius groups that show that it's sharp, and if it's not Frobenius, you can even jump to 2 over n, so that's a very nice result. And then somehow I made this conjecture many years ago, independently. Boston and his co-authors also made it. And so this is a kind of an intuition that the proportion, although we already get something nice here, that if we take a finite simple group, the transitive permutation group, then the proportion of derangement should be much, much larger. It should be at least epsilon for some fixed epsilon positive. Okay, so and there has been a lot of work and a lot of progress on this. So let me introduce some notation. Let's say that DG is a set of derangements in G. Note that this is it's close to taking inversion. You know, the inverse of a derangement is a derangement. This is useful. It's a normal subset. This is why it's kind of even if you restrict to normal subsets and start two-step situation, this is why partly why it's useful. And the conjecture states that DG is epsilon G. Obviously, if we take H, a point stabilizer of the permutation group, of then DG is the complement of the union of the conjugates of G, which are all the point stabilizer. This is trivial. And so a very nice result of Bob and Jason is that the conjecture holds, and it took a lot of time. They worked on it for, like, from the announcement to the publication of the last paper, it's 16 years. And they even found an explicit and not very small epsilon, which works for all large enough some finite simple groups. But we don't know what large enough means, I think. Okay, so now we are interested in derangement width. And this already, namely, if we take the set of derangement and we take small powers of it, when do we get the whole group? So already we have an easy corollary of the result of Bob-Jason, and simply to apply Gowers trick. You see, we know that the proportion of derangement is at least epsilon. And by Gowers trick and by the fact that finite simple groups are quasi-random, we immediately get that for sufficiently large transitive simple permutation groups, every permutation is a product of 3 derangements. So that's already nice, but our ambition is to get 2 instead. So okay, so at least for interesting families of finite simple groups, there is this result which follows from previous results. Let me mention the result and show you why it follows. So G is a finite simple transitive permutation group, and suppose it's alternating or of Lie type of bounded rank, then every element of G is a product of 2 derangements. Okay, so this is what we wanted to prove, and at least we get it in this result for various families of finite simple groups. And as I said, the proof is quite easy, because for the groups above, both for alternate groups and for bounded group, for bounded rank groups, we have that T square is G for normal subsets, and of size at least epsilon G, and so combination of the combination of the Bob-Jason theorem with our previous solution to question 1, positive solutions to question 1, give us at least half a solution of the problem, if you like. And now it remains to deal with classical groups of unbounded rank. So we may assume a primitive action here. We may, otherwise the point stabilizer will be larger, and there will be everything goes in our favor. Okay, so in this context of derangement with and tools which I would like to introduce, let me give you some background. There was a conjecture of Peter Cameron that almost all permutations in Sn do not lie in a proper transitive subgroup, namely a transitive subgroup which doesn't contain A. So that's a famous conjecture of Cameron, and Thomas Wuczak and Nazi Pyber proved it in '93 in a very nice paper, and so they proved that the conjecture holds. By the way, this is also related to invariable generation. They establish results, and Eberhard, Ford, and Green have a better result, and also Perez and his co-authors, and it's a very active area. But let me also mention that Wuczak and Pyber, this is not the right way to write Wuczak, but I don't know how to do it in tech, so maybe someone will teach me. There should be some line. Anyway, so in '98 I addressed the question asked by Wuczak and Pyber, and showed that almost all matrices in G and Q, Q is fixed and n goes to infinity, do not lie in a proper irreducible subgroup, namely not containing SLN Q. Okay, so that's answer question Wuczak and Pyber, but I didn't know how to do it for all classical groups, and it took 20 years. Fullman and Guralnik did it for all classical groups. So they proved a similar result. The union of all reducible subgroups is negligible. For classical group of rank going to infinity, they have a better result because Q is not fixed here. It can also go to infinity, so it's better than the previous result, even for GLN. There is an exception that the symplectic group, characteristic 2, they have these maximal subgroups. these are large if you take the union of the conjugate, so you omit them in the case of these groups. Okay, why is it relevant? Well, first of all, it's interesting in its own sense, but a corollary now is that if G is a classical group, then it has derangement with two, namely everything is product of two derangements. If it has a large enough rank, and H is irreducible, and it's not this subgroup which I pointed out earlier. Okay, the proof is now really trivial. I assured you that I will also use an absolutely trivial tool. Simply, the union of the above subgroups, if n is big enough by the previous, by the Fullman-Goralnik result, the union is negligible, and therefore the complement of the union is big. So we can, if we take the point stabilizer of such subgroups and we take the union of the conjugates, it's inside X of G, and the X of G for n big enough is of size less than G over 2, therefore this is of size more than G over 2, and we have seen trivially that this implies that the square is this set of derangements is everything. Okay, so sometimes trivial arguments help if you have strong results to combine them with. Okay, now how shall we proceed to get more positive results about the derangement with two question? Okay, so first of all, I claim that there are absolute constant C1, C2 such that if here we have a classical group, and again with this exception, and n is at least C1, so the dimension of the natural module is not too small, and the action is not a subspace action on subspaces of dimension, of small dimension, of dimension at most C2, then G has derangement with two, namely everything is a product of two derangements. And this also follows quite easily from the work of Bob and Jason. The idea is that we may assume that H is reducible because of the previous theorem, of course, so it acts on subspaces. And we can take, say, k-dimensional with k at most n over 2. And then another result of Fullman and Goralnik is that as k goes to infinity, the proportion of derangements in such action, subspace action, it's 1 minus big O of k to the minus 1 over 200, if I'm not mistaken. But this is good enough because, when k goes to infinity, this goes to 1. So we are done as before. So there are, so many derangements. The square of them is everything. Okay, so we are left with subspace action on bounded dimensional subspaces where the dimension of the maximum of the natural module is very big. Okay, so in the remaining cases, we also have various results, and the idea is to use character methods again, and in a way similar to the methods of a famous paper by Males, Axel Weigel, where they proved, for example, generation by involution and another element of finite simple groups. And there are also various other researchers and papers deal with extensions of this method. For example, there is this work which I mentioned from 2011. There is also work by Goralnik and Male and others. So essentially, the idea in the remaining cases is to use the what we call weakly orthogonal tori T1, T2, and to find regular semi-simple elements in them, little t1, little t2, such that only few characters satisfy that the character value both character values are non-zero, and this from the structure of constant, the Frobenius formula, if you like, this helps a lot to show that if you take the conjugacy class of T1 and the conjugacy class of T2, you multiply them, that you get everything except the identity, maybe. So that is a strategy in the subspace action cases. And I should also mention that we are looking into situations where we can show that these few characters are also unipotent, and you have a lot of understanding of them. Okay, so what is the upshot? We don't have a complete proof yet. So, but we hope to have it soon, and so we hope to complete this project. It's actually an ongoing project, and you know, if this conference had been cancelled, then we would have more time. But anyway, so what happened? So we made a lot of progress on also in the remaining cases, but not enough to declare that the problem is solved. And we are working on completing it. And let me. So you see, what we hope to prove is that possibly with finitely many exceptions, every element of a finite simple transitive permutation group is a product of two derangements. But I'm also asking myself whether there are exceptions at all. So this is a nice question for people who know computational group theory. I don't think it was even checked for all the sporadic groups or something like this. So I don't want to make a conjecture where we don't have enough information. I strongly believe that what's written here is true and will be shown to be true. But about conjecturing that there are no exceptions whatsoever, I don't know. Probably some people will make some computer experiments and will be in a better position to make a conjecture. Anyway, thank you, and take care, all of you. Yes. Yes, actually, I think even more ambitious project is to classify primitive permutation groups in which every element is a product of two derangements. Even three derangements might be interesting and trivial in this case. We didn't think much about the general primitive case. We know that there are examples, there are counterexamples. I mean, for example, Frobenius groups are not nice here. There are some counterexamples, and it is a very interesting project to even generalize, you know, from the simple case to general primitive case. The answer is no in general for primitive groups, but you know, sometimes let me convince you. Sometimes the set of derangements is a proper subgroup. So you know, you cannot multiply it with itself even million times and hope to get the whole group. So, and that's the case in Frobenius groups, right? Because they are all in the Frobenius kernel. So, so that's why I'm saying that there are counterexample to the more general question. But still, I think that it might be possible to obtain progress for primitive groups and to locate the abstractions, prove positive results in the other cases. That would be very interesting. And you can. I see. Is it on the archive already or what? I see. Anyway, whenever it's ready, I would be happy to see it. And that's already encouraging that you classify the cases where the derangements generate a proper sample. I see. So one of them is probably the Frobenius groups, right? Or I see. Yeah. Yeah, that's intriguing. Thanks. Thank you, and I hope to see you all soon.